recap again. Um, Today I'm going to present about the topic ultra high performance fiber reinforced concrete. In abbreviation, we call UHPFRC for prestressing applications. My name is Htike and my student number is 67720414121. This is a take-home exam for the course 2101615, Advanced Prestressed Concrete Structures. So let's jump into the presentation for now. So we do have two parts for this presentation. For part one, I will be discussing about what I learned in advanced prestressed concrete structures, and I will tell you what is the HPFRC and some motivations for this one and limitations of conventional prestressed concrete. And then for part two, I have some material properties and structural behavior of UHPFRC, and we have design considerations, and I will describe two case studies already presented in the report, but I will highlight some of important parts for these case studies in this presentation. So let's talk about the review for this prestressed concrete. So this is a review of prestressed concrete. We have known that the reinforced concrete tensile strength is limited, while the compressive strength of it is extensive. Consequently, prestressing becomes essential in many applications to utilize fully that compressive strength and control cracking and deflection through proper design. So as I have mentioned now, to improve structural performance, prestressed concrete is an advanced structural system in which internal stresses are created prior to the application of external loads. To balance tensile stress that comes under surface loading, the main aim is to place the concrete part in a favorable stress state, usually compression. That's why we use prestressing, which improves fracture control, stiffness, durability, and ultimate load capacity, as we know that concrete is strong in compression and weak in tension. So let's talk about some basic concept of prestressing. So here in this slide, you will see that this is the pretensioning process that I saw in Saraburi, Thailand, last November 4th, 2025, when we go to the site visit for SCG. So I saw that high strength ski tendons are tensioned in pre-stressed concrete members either prior to concrete casting, which is called pre-tensioning, or following concrete hardening, post-tensioning. As we see here, there's a pre-stress pre-tension condition. And then in the class, we have learned about the transverse stage and service stage and ultimate stage. So for this one, we know that before pre-stress transfer, concrete experiences with no load and tendons carry full tension. For after transverse gauge, compressive stresses are present in concrete, generally uniform in pre-tension elements and more localized near anchorages in post-tension. And the surface loads, pre-stress induced compression, it reduces tensile stress caused by bending. The tensile stress remains below the cracking of concrete threshold. So after under ultimate loads, once the tensile capacity is exceeded, cracking starts and the behavior transitions toward flexural behavior governed by tendon yielding or concrete cracking. And I've learned some immediate losses, which are elastic shortening, anchorage slip, and friction losses. And then I have learned time-dependent losses, which are quick concrete, shrinkage, and relaxation. So let's go back to the main topic, which is called UHPFRC. Here, UHPFRC, as the name, ultra high performance fiber reinforced concrete, it is a high performance material with significantly higher strength, ductility, and durability due to its dense microstructure and fibers, allowing for slimmer designs and reduced material use. So why are we going to use that? Conventional prestressed concrete uses high-strength steel tendons to create internal compressive forces in a standard concrete matrix to resist tensile forces. But for UHPFRC, improved material properties provide a more advanced, durable, and often more detailed alternative that can be used to design more slender structures. So as we see in this photo, in this picture, this is a UHPFRC girder after a flexural failure, where a confined UHPFRC zone forms a highly ductile plastic hinge region instead of a brittle concrete crash zone. This made it integrated around the reinforcement, preventing explosive swelling and delaying failure, while cracks develop in a controlled pattern, as we see here like this. So this behavior demonstrates how UHPFRC significantly enhances the formation capacity, crack control, and safety in pre-stressed or reinforced concrete gutters. Okay, so let's talk about some main problems in conventional pre-stressed concrete. So some problems as I list here are seen for conventional pre-stressed concrete, such as early cracking due to design weakness. We need the grade cover requirements for durability, and like pre-stress losses that I discussed in the previous slide, shrinkage, creep, and limited lifespan in aggressive environments. For this case, we have less cracking properties and thinner cover, longer service life, and improved stress retention and more efficient structural members for higher ultimate capacity. Okay, so let's jump into the part two, the main topic of this presentation, UHPFRC. So let me discuss some about UHPFRC. UHPFRC is generally composed of high amounts of cement and silica fumes, such as binders, steel fibers, and low water and binder ratio, and admixtures such as water reducer. UHPFRC has low water to cementitious materials ratio, which is 0.18 to 0.125, and dense particle packing. So we may have almost no shrinkage or creep, making it suitable for concrete members and the long-term loading. And it also introduces the significant enhancement in the sustainability of concrete structures due to its dense microstructure and damage tolerance characteristics. Okay, so this is just a concept of UHPFRC. For here, let's talk about with numbers. You see that for conventional concrete and UHPFRC, we see a lot of difference between the ultimate compressive strength and early compressive strength and flexure strength and shear strength. For this wall, you can see the higher properties compared to the conventional or normal concrete. That's why we can assume that it has better bond properties with pre-stressing tendons, less creep and shrinkage than ordinary concrete, post-cracking totality. And let me discuss about this stress strain diagram, which is called UHPFRC over here. And we see that here, this is a fast cracking point over here. It behaves elastically before cracking. And then it has a first cracking stress. And then we do have multiple cracking stage, a strain hardening because it's due to fiber region. And then we can see that there will be a multiple fine cracks. It's not that one big crack. And then we can see the peak tensile strength over there. And then after this pepper stage, we have the softening branch, which is called, and here we can see the crack localization. So here we can assume that we have much superior tensile performance compared to normal concrete. So let me talk about the motivation using UHPFRC. So as I said before, we have the best tensile performance strength. So it is highly compatible with the safe application of larger pre-stress levels, the reduction of pre-stress losses, the minimization of cracking, or even elimination of cracking during service loads. That's why I think UHPFRC is a suitable material. And we can see that this is a structural behavior of UHPFRC members. So the material's high compressive strength and enhanced design capacity, remarkable longevity have a significant impact on the structural behavior of pre-stressed UHPFRC members. So let's talk about this photo first. Here, this is about the uniaxial tension, the strain hardening, the strain softening. So this is about the black curve you can see here. It's a strain hardening response after initial cracking stage. The presence of fibers allows the material to sustain increasing load with increasing deformation. And the blue dashed curve, this is called a moderate response, where some hardening occurs, but is limited by insufficient fiber engagement. And the red one represents strain softening. After the first crack forms, the tensile load decreases because crack localization occurs immediately. This typically happens in misses without fibers or with inadequate fiber distribution. The gray one, like this is just visually reinforced that specimens without fibers fail abruptly, while fiber UHPFRC shows enhanced post-cracking resistance. This stage is called 3-point bending stage for low deflection behavior. And this black curve represents deflection hardening, and this blue dash curve represents a partly hardened response with limited totality, and the red dash curve shows deflection softening. And as I have mentioned before, these sketches show that without fibers, the beam loss load immediately after cracking, resulting in brittle failure. With effective fiber reinforcement, the beam can undergo larger deflections while maintaining or even increasing load capacity. And this one is about my simple calculation of the beam and the uniform load using UHPFRC. Here I have these dimensions. Here you can see that I introduce the elastic modulus in Pascal, which is much more than normal concrete, 55 into 10 power 9, which means 55 gigapascal over here. And then I can see that this low deflection curve over here. So for this one, I think that all calculated stresses remain well within UHPFRC limits, indicating excellent structural performance and crack control under typical pre-stressed concrete loading conditions. The full MATLAB code is in the appendix of the report. And this is about some codes and design classes using UHPFRC. So we have, I saw some codes in the literature that we have NFB 18470 from 2016 and 710 and then 451 from 2018 specifying UHPFRC. The first one, material and requirements and constituents and mechanical properties. And then for this 710, we have common design code standard, which is linked to Eurocode 2 because these three codes are from France. And then we have candidate over here for UHPFRC guided bridges, focusing on structural performance. We will assume it as a case study in the next slide. And then we have this one in Thailand. There are no widely accepted guidelines internationally, but for materials used in those mixes, obey local standards such as DIS 152547. Okay, let's go to the two case study. The first one is the flexural response of pre-stressed concrete beams. So there are 5 beams with varying lengths of UHPFRC layers and 4-point bending, exploring effects on load capacity, stiffness, failure modes, and more. And we can see that this load deflection graph clearly shows the superior structural performance of the UHPFRC beams compared with the conventional control beam, the black curve. So it has a lower peak load right here and phase early with limited totality. In contrast, all HPFRC beams, the red one, the green one, the blue one, the yellow one, exhibit significantly higher load carrying capacity and much larger deflection before failure. This graph highlights that UHPFRC improve both strength and deformation capacity, making it highly suitable for pre-stress applications where high totality and crack control are essential. And then this is a result of observations of the experimental work. And there are some parts he highlighted in this paper. And we have the strength performance up to 65% improvement. And ultimate load capacity is significantly increased. Here you can see 159% increased. And then we have the stiffness improvement up to 88%. So we can see this in this case, this UHPFRC beams commonly fail by concrete cover separation. It indicates a stronger core material. And in this paper, he suggests that we need more information and we need more improved detailing at the cover reinforcement zone. And this is a case study 2 I have mentioned before, using Canadian Highway Bridge Design Code. Here, this is a stress strain diagram for the ultimate limit stage of flexural condition in HPFRC girders. Here we have the compression zone behave linearly until peak, allowing the larger compression strain, which is 0.003 right here. And then we have the neutral exit position shifts depending on section geometry. And then prestressing steel remains in high tension at ultimate, and the stress block configuration changes with flange thickness. And then we have the equilibrium of forces, carbon failure, ensuring the section reaches flexural capacity only after full development of compressive strain in UHPFRC and yielding of prestressing steel. In this paper, he also introduced the iterative procedure for this design, for the bridge design. So in prestressed girders, this is very advantageous because of its mechanical properties. This paper also emphasized this innovative approach aligned with the modern design codes, supporting efficient and durable bridge design. Okay, so let me recap this presentation. So why are we going to use UHPFRC? Early age cracking, low design strength, and long-term durability problems are the common ones with conventional prestressed concrete that limit its lifespan and structural effectiveness. The usage of UHPFRC is driven by the requirement for the materials withstanding increased stress levels, reduce cracking, provide more robust, slender prestressed members. So, and then we can also see that it also leads to overall reduction in dead load of the structure, decreasing shrinkage cracks, particularly in deck slabs and prestressed girders, which are already studied in the case tube. Despite its high performance, UHPFRC require careful attention to material protection, curing processes, encourage detailing in case one we have already learned, and time-dependent behavior such as creep and shrinkage. The paper also suggests that the further work should be the application of more prestressed structural components using UHPFRC. So thank you so much for listening to my presentation, which is about UHPFRC, ultra high performance um, for prestressing application, ultra high performance fiber reinforced concrete. In abbreviation, we call UHPFRC. So thank you so much again, and ขอบคุณครับ